Hello, my name is Carmona, and in this talk I would like to present our work on scalable modularized Bayesian inference and introduce a couple of ideas in the context of Bayesian data integration and model misspecification. This work is a collaboration with Jeff Nichols. We're both based at the University of Oxford. Now, there are two main takeaways after this short talk. First, I will introduce an inferential framework to deal with model contamination that we call semi-modular inference, or SMI for short. And second, I will propose one way to implement such framework in a scalable way, so we can explore optimal rates of feedback between modules more efficiently. The presentation is based on the poster that you can find in the symposium website. To begin with, let's say that we're interested in models that are made of several modules. We can illustrate such situation with this canonical example, where we have two data sources, Z and Y, and let's suppose that we have a model for this data, which depends on the link parameter phi and module-specific parameters theta. This framework can be extended both horizontally for more data sets or vertically for hierarchical modeling, but let's keep it minimal for clarity. We can perform Bayesian inference to learn simultaneously from all the data and update our beliefs about the model parameters. The conventional posterior would be as shown here. This is a very common setting in a number of real-world applications that are interested in combining multiple data sources, and such applications include epidemiology, ecology, economics, and many more. However, it's been observed that such multimodular settings are prone to model misspecification, and in particular to model contamination. Any badly specified module may distort the inference of the model as a whole, leading to bias, incorrect variance estimates, poorly calibrated uncertainty, and many other undesirable effects. So we'd like to find a way to optimally combine the data, but without doing more harm than good. Now, two well-known modifications to the posterior, which aim to address these problems, are one is modularized inference, or also known as cut posteriors, which eliminate the feedback between the feedback from suspect modules. So let's say that in our example, we suspect that the module for Y is misspecified, and we can eliminate its feedback into phi by modifying the posterior of phi to only learn from Z. A second option is to use power posteriors, which reduce the relative importance of some likelihoods assumptions in the learning process by raising to a power eta. Now, recently, we've proposed semi-modular inference, which unifies these two approaches in an encompassing framework. The idea is to be able to tune, rather than eliminate, the influence of individual modules in the joint learning process, allowing to aggregate evidence while caring for model contamination. The SMI posterior is characterized by eta, the degree of influence of each module. In our AI stats paper, we discuss theoretical details of the framework. We show that it is a coherent update of beliefs. We implement it using MCMC and discuss some ways to choose the optimal degree of influence eta. Now, to clarify the idea, the SMI posterior can be represented graphically as an unfolding procedure and learning in a two-stage process. So using our working example, when I unfold this graph, I create a copy of the parameter theta and the data y. In the first stage, we learn the parameter phi and the auxiliary theta tilde using a tempered version of the modules using the power posterior. And then in a second stage, we'll relearn the module-specific parameters theta conditional on the posterior for phi. Notice that the SMI interpolates between the conventional fully based posterior when eta is equal to 1 and the cut when eta is equal to 0. And this generates a family of inference procedures indexed by eta. Now, current implementations of the cut posterior and the SMI are based on MCMC, including some new advances in unbiased sampling using couplings by Pierre Jacob. The SMI framework can be applied to large models with more than 2 modules. And so we can vary the degrees of feedback between them. But exploring such multidimensional space would be very expensive using MCMC, as there is one posterior associated to every choice of eta. One scalable option is to use stochastic variational inference and minimize the KL divergence using a Monte Carlo estimation and then stochastic gradient descent. However, this can't be done directly because the modular posteriors have multiple intractable terms, which act as conditional normalizing terms. So for instance, in the cut model, we have this P of y given phi, which is intractable. But we realized that the trick is done by defining the variational family as a product of 2 distributions with independent set of parameters and carry out the minimization of the divergence in 2 stages. First, we approximate the power posterior to obtain alpha and the variational posterior for phi. And in the second stage, we approximate the conventional posterior, but holding the marginal of phi unchanged. And this will yield the parameter beta. Now, the final ingredient is the choice of the functions q of alpha and q of beta in the variational family. We propose to use normalizing flows as they offer remarkably expressive probability functions that can be used for scalable variational inference. The main idea is to define a base distribution as well as 2 transformations, G1 and G2, which are invertible and differentiable, and their inverse is also differentiable. And then transforming the base distribution using G1 and G2 will define our variational family. For our particular purpose, we can use autoregressive neural networks for the marginal posterior of the link parameter phi and a conditional autoregressive neural net for the module-specific parameter theta. The parameters to optimize here are the weights and the biases in each neural network, which would correspond to alpha and beta in the previous slides. Finally, I would like to share some images of the variational SMI in action. We have tested this framework in a number of applications, and here I'm showing the results for a well-known epidemiological study that analyzes the correlation between human papillomavirus prevalence and cervical cancer incidence. We obtained very positive results, reducing execution time dramatically, but yet preserving good approximations that are comparable to MCMC sampling. Now, in the bottom panel, we show the relation between the HPV prevalence, or phi, and the logarithmic yearly rate of cancer incidence for the 13 groups in the study. The dynamics of the plots illustrate various degrees of influence eta, going from 0, this is the cut posterior, to 1, the conventional posterior. In the right panel, I show the slope and intercepts of this relation, which are theta 1 and 2. Code and more details are available in my GitHub and are reproducible in Google Colab. Well, thank you for your time, and please feel free to contact me if you are interested or have any question. And here are some references, including our recent AI Stats paper. Thanks.